Good to be here. So we're focused on machine learning, all right? We'll take a data approach, but this is a machine learning thing. So our goal is to improve a machine learning model. The goal is to have a machine learning model that works on the real world, on real data. And that's the focus. And how do we do that with the current situation in terms of architectures and what's out there in terms of data? We're focused on automatically finding and fixing data and label issues. So the idea is systematic, automated ways to do this, not human-driven. I spent a lot of time on this, about 10 years, and I say this because just like you guys, I care about my time. So a lot of this, the first half of this is going to be focused on why would I do that? Why does this seem to be really important? I built the cheating detection system at MIT and Harvard, and a big issue we face there is with false negatives and false positives. How do you know for sure that someone didn't cheat? How do you know someone didn't commit a crime? How do you guys know I'm not lying right now? It's very difficult. So we assume innocence until proven guilty. And so it's a very difficult machine learning task because you have a lot of labels that are 0, but they might actually be 1. And it turned out at the time that machine learning did not work for this task. There was no machine learning algorithm that was generalizable for multi-class standard classification that worked with noisy labels. I found that shocking. The machine learning doesn't work on real-world data. I thought that was really wild. So I spent my whole PhD trying to solve that problem. This is solving, not solved, but we've made a lot of headway, quite a bit, and we'll focus on some of that. So this is focused on lessons, and I'll go through 6 lessons. The first 5 are sort of motivational. The 6th one is how do we solve it. And the first lesson is that the best model is only as good as the data it learns from. So I don't know if you guys have seen this article, but it says when algorithms mess up, the nearest human gets the blame. And I'd like to try to reframe this and think about this paper that many of us have seen, which basically says garbage in, garbage out. If you train a machine learning model on data with completely random labels, it will produce predictions that are completely random. It's a great model. It works perfectly. It can be hyper-parameter optimized. We can use all the greatest and latest, and you'll get a model that gives you complete garbage because it's trained on garbage data. And so I just like to reframe this and say, instead of when algorithms messed up, what if instead we said when algorithms are trained on erroneous data? And so it's a different way of thinking about the problem. The second lesson is that data and label issues are plaguing some of the most used AI tech right now that's really hot. So we'll look at a few examples that you guys will be very familiar with. OpenAI has openly stated that some of the biggest issues with DALL-E and GPT-3 are label issues and data issues. So we'll look at a few quick examples. This is from their tutorial video on DALL-E 2. Show of hands, who knows DALL-E? Image generation? Okay, sweet. Yeah, so you can just check this video out for yourself. But pretty much like the main issue that they talk about throughout the video is that it will randomly generate random images because it was trained on data that was different labels. So you had an avocado and it was labeled cucumber, and then you say, give me an image of like, a cucumber, and it gives you an avocado. And this actually happens quite a bit. It's just bad labels. But how do you look at millions of data and find all these labels and train on good data? Another example, so this is just more examples from that. Another example is ChatGPT. Many people know this already, but the whole idea was to take GPT-3, and then the biggest issue was that there was a lot of like untruthful and biased and harmful data. So they had humans actually go through, label the quality for each, and then retrain it on high quality data. So the biggest issue with GPT-3 was really on the data side, not the machine learning algorithm. There weren't that many innovations on the machine learning side. It was really, how do we actually automate this process? And at the time, they're using humans to actually check and label things and give quality scores. But how do we automate this process of taking data that's bad and biased and has problematic outputs, and then train a model in a smarter way on better data? So it's the same idea repeating over and over. And we're seeing this across the industry in the most pervasive technologies. Every major tech company struggles with this problem. So just personally, I have done an internship or contingent research position or some kind of position at Meta, at Oculus Research, at Google, at Amazon, at Microsoft, and same problem over and over. That's what I worked on at all 5 places. This is pervasive across the industry. If you guys have seen this article, Andrew Ng basically saying that 80% of like the time spent in the machine learning pipeline is actually just improving data quality. And then there's lots of articles talking about how much this costs the U.S. and the economy, but that it should be solvable. Have you guys seen this by Andre Karpathy? This is Tesla's data engine. This is how they train their machine learning models for self-driving cars. And really what it comes down to is they have, their car driving, and then they do it in an area that they don't have a lot of data on. So this is a tunnel. It's very dark. They don't have a lot of data in that dark tunnel. So you're driving in the tunnel and the car starts doing weird things. And so what do? Well, they have to get that data and then generate a bunch more by collecting more data of that type. And then they have to label it and then train it and do this repeatedly. So imagine if instead you could actually go through your data set and know, hey, this is all my low quality data. This is all the stuff that my model's not going to do well. I can augment this ahead of time instead of deploying the car, having it crash and wreck a bunch in tunnels, and then repeating this process. So that's what you'd like to automate. You'd like tools to try to automate this. This is a really great image. And I think a good way to think about this is imagine like Elon Musk comes to you and he says, all right, Andre, I need you to get this car to just work for stoplights. And you think, okay, that seems pretty easy, like green light, go, red light, stop. And then you go out in the real world and data is like totally crazy, right? Like this is stoplights all over the world. And so the reality here is that data quality is very complicated and data is not always what it seems. Sometimes labels are not as simple as green light, red light. And so what do? How do you handle this situation? And in this case, these would be identified as outliers, and there are automatic solutions to do that. And they can be identified as low quality labels and hard data, and there are lots of ways that we can solve that in automated ways. This is a great slide that Andre shared in the same talk where he says, all right, this is the amount of time I spent in my PhD, and this is the amount of time at Tesla in terms of data sets and machine learning models. And so you see this transformation as you go into deploying these things in the real world of how much time gets spent on the data versus the machine learning model. And there's a bunch more examples you can check out. You can check the slides out later. So the fourth lesson is that, and this might be a surprise. I'm actually curious, how many people know of this result? Sweet. Cool, yeah. It's pretty wild. If you look at the top 10 machine learning data sets, this is the test sets that we've been benchmarking on as a field. Okay, so this is like what the test sets we've benchmarking all our algorithms on, from like the top institutions in the world that are doing machine learning research. And it turns out that all 10 of them have errors, like sometimes pervasive errors. We looked at the Google data set, which is Google Quick Draw, and it had at least 10% label errors. So you're benchmarking on these things. You're saying this is the best model on this data set, but that data set totally has wrong data in it. And so how can you trust those benchmarks? These are just a few examples from 5 of those data sets. The Google Quick Draw one is on the right, MNIST from Jan LeCun on the left, CFAR, Caltech, ImageNet. These are all label errors that are just in those data sets, just bad data. And previously there was no way to really find these things automatically. And so we started focusing on that problem, seeing how we can solve that to improve machine learning models at scale and in production. And this is a table where you can see all of those tabulated across the 10. There's a website here if you want to check them out. I won't go through it. It's a lightning talk, so we're going lightning speed. But you can check that out, labelerrors.com. And there's 10 different data sets there, including audio, image, and text. Fifth lesson, your test benchmarks might not reflect real-world performance. So let's look at a quick graph. On the left, you see a model that has 100% test accuracy. But actually, there's some bad data mixed in there. So here, the inside is the true label and the outside, or the inside is the observed label and the outside is the true label. And so it turns out that actually this model that looks like it has 100% test accuracy, say it was a car, and you put it out in the real world, and there's a cliff and there's not a cliff, and this is like the probability it goes over the cliff, then like in the real world, it's going over the cliff a third of the time. It's going to be very costly. And so it's really important that your test data sets have accurate labels or you can't trust your benchmarks. So the sixth is how do we focus on solving these problems? And so I'll chat a bit about what we're doing and sort of the underlying mechanisms and the research behind it. Some of the initial algorithms and research that was done in order to solve this problem that was then productionized is called confident learning. It was initially inspired by things from information theory and quantum computing. The key idea is that you want to have a theoretically grounded solution. Like if you're going to say this is label errors, can we actually prove, at least for certain data sets, that we can exactly find label errors? And can we say for other data sets that we have some confidence that we'll do a good job? And so there's a lot of theory behind this. The inspiration from quantum computing, if you guys are familiar with NMR, quantum computing, I don't know, it's like getting more esoteric for this conference, but my PhD advisor, he built the first quantum computer, Isaac Chuang. Cool guy, I worked with him for like 8 years, and I was inspired by him. A lot of the key solutions for quantum computing where you have a quantum computer, you do a bunch of simulations, and what you get to measure is a noisy signal. And so you end up with a data set that's like a bunch of sort of states of the quantum computer, but there's a bunch of errors in there. And so what you do is you actually estimate what was the noisy channel that got you what you observed, and then you can reverse engineer that noisy channel. It's just a matrix of flipping rates to figure out what the original computation was on the computer, and then you can actually estimate the computation that's happening on the quantum computer. So that's how that works. And I thought, hey, we can do the same thing with any arbitrary data set. That's just a data set. So it should work for images. It should work anything that you can represent as numerical data with labels. It should work. And we applied that. We spent a lot of time on that, about half a decade, and we were able to pull this off. And so that's kind of how Cleanlab got started. And that's the underlying mechanism behind it. And so there's a paper, you can check it out. There's a bunch of papers on this now. But what's neat about this is that it works with any model, any data set, and any modality. So it's not specific to like images or text. The goal is to solve this problem for any sort of data set. And there's a bunch of stuff on this. This is not just for random label errors. The idea is like a dog is much more likely to get mislabeled as a fox than as a bathtub. And so what you want is something that works for systematic issues, like systematic errors in data, like with the real world. And so this is a solution that works for that. I'm going to skip the math notation. I've kept it in the slides for those who are interested and who want to look at this later, but it's a quick talk. At the end, you get an estimate. So this is something you want to estimate. This is basically the joint probability of any two sort of mistakes co-occurring. So on the left, you see, for example, like a noisy label fox, and then on the top left, you see true label dog. So this would mean that if you had like 100 examples, that 14 are labeled fox, but should be labeled dog. And this is the thing that you estimate using confident learning, and then we build a lot of algorithms on top of that. This is a really quick demo that shows this equation is like, let's look at the probability of an example. If it's greater than some threshold for each class, then we can say, hey, it's probably labeled that thing. And so you can go through a data set, and this is showing a simulation, which in a lightning speed talk, you can only go so far. But I just want to show you that you can filter out a data set into that matrix I mentioned. And what ends up happening is that the things on the diagonal are the things labeled correctly, and the things on the off diagonal are your label errors. And you can then get actually a confidence and guarantees about this. For certain data sets with certain assumptions. And then with other sets, you relax those assumptions with other data sets. And you can check that out after. So these are, for example, the two label issues that are detected using this method. I don't know how much are you guys into this math stuff. I don't know. I don't know if I've got the right audience. Yeah. Maybe I'll leave this one for later. This is a quick proof that just shows for an arbitrary machine learning model, like ones that you guys are using every day, they don't produce perfect predicted probabilities. So you can show that that the algorithms that we build on work perfectly for perfect predicted probabilities, but most models are not perfect. And so what happens is like, how does this stuff work when you have, for example, like a miscalibrated model, or a model that's producing erroneous predicted probabilities, or a model that's spitting out, like, say it's always really confident in dogs. It's seen lots of dogs, so the probabilities for dogs are like a little bit high. And this will show you that you get exactly the same result. You can still guarantee perfect label error finding. I'll let you check that out later. It's a really simple argument. Okay, so this is a table showing a bunch of methods, like this is the one out of Google, this is the one out of Facebook, and then it can just show how these methods outperform those. A key thing about this table is that on the right is much more realistic. That means the 0.6 means that most of that matrix is like 60% of it is zeros. That means most of the flipping and like errors is only in a few classes. That's very realistic and much harder. That's what the real world's like. And so what we show is that using these methods, you get the same improvement in your model regardless of how realistic. So in the most realistic scenario, you still get the same improvement, whereas you see a massive drop-off in most of the sort of primary text solutions. Cool. So just a quick few things. If you guys like open source, there's a bunch of stuff in the Cleanlab package you can check out, and most of it's like one line of code. So everything I just showed you can be found, can be run. In some production, and you can check this out. Find label issues is a way to find label issues. You can also find outliers. You can also find the best consensus label if you have a bunch of annotators. And these are all sort of one line of code algorithms. That's what we go for, or like a few lines of code. And what's neat about this is it works for any data set, many data formats, any data modalities. So it's a very general solution. There's a big gap between sort of having your data and it being lower quality than you want, and then the deployed trained model that works in production. And so the whole thing that we're focused on is how do you take that low quality data and get to a high quality model, and that's what we do. And so that's what our whole company's about, and building an enterprise solution that gets you from A to B. So what's neat and different about us, we came out of MIT, spent quite a while on this at MIT, and then 3 PhDs founded the company. And we publish research, which is pretty different than most startups. We had 5 papers in ICML and NeurIPS last year. We publish research blogs, and we do a lot of open source. So there's 2 things you can check out on your own, and appreciate your time.